Okay, now we're going to go ahead and we're going to breadboard a parallel circuit. So same breadboard layout, all right. I still have my black and my red going into this long blue line here because all those connection points are the same, and I have my red going into the long red line. All the connection points are the same. All right, on the breadboard, nothing's changed here. Everything in this specific row, so this is row 55. This is the same connection as this hole, so there's 5 holes here. They're all giving the same signal. They are not the same as these 5 holes that read across here, though. This divider's here so that we can do our IC chips, our integrated circuit chips, and we can put them across in the same row situation and they won't short. We'll cover that in a different video where we do those. But let's go ahead and get going on our parallel circuit. All right, so I'm gonna run this circuit, and we're gonna go over here. We're gonna come from positive, all right, as we'll just kind of give it that common nomenclature here, and I'm gonna put that in the red on the far left hand side, and I can put it anywhere. I could put it in the red here, I could put it in the red here, I could put it in the red here. All right, we're gonna move this around. We're in the red here. So let's move this down. I'm gonna put this where the 40 is. All right, just so we can kind of see. Good habit of breadboarding is keeping the wires flush and flat. I should trim this so it's, you know, a shorter connection from here to here, so it's more flush. And then I'm gonna turn this outside just so you guys are gonna be able to see better. So I'm just going from red over here, and I'm going to go into the hole 40 here. Now, I'm going to take my different LEDs. All right, I'm going to start with my amber one. And please remember the LEDs. The shorter leg is the negative side, or the cathode side, and the longer leg is the plus side. And then, if you look closely, you'll have to have an LED in hand, but it's flat on this edge right here. So if you cut the LEDs, you'll still know that the flat edge is the negative edge here. So I'm going to go from red, which I'm going to call positive here, to negative. So I'm going to put the long end of the LED into the same row that the red is coming into from over here, the plus, all right? And then I'm going to, so it's easier for us to see, I'm going to take the negative lead and put it into pin 45 there, all right? So this is my first LED here, and I'm going to put it in parallel, which means I'm going to do the same thing in the same rows. So the long end of the LED is going to go over here in this row with these guys, and the short end is going to go over here in the same row that the amber one is sitting in. Okay, and then I'm going to do the same thing with the green LED. All right, long ends up here, short end down here. All right, that's so if I turn these LEDs, they wouldn't work because they're diodes, light emitting diodes, so they only allow current to flow in one direction. So I have all the long legs in row 40 up here, and I have all the short legs in row 45. Now I've got to complete the circuit. So I got to take a wire from row 45, and I'm going to put it into the blue, all right, or the negative, and it's going to complete the path. All right, so what's going on here? Only one of these comes on. So we could have an issue of not enough voltage to supply all these. So I'm going to mess with this power supply, and the power supply is doing good. Is it the power supply? Absolutely not. You know what's wrong with this? And they're smelly, and they're going to blow, and you guys can't smell that, obviously. But what's happening is with the power supply, I didn't put a drop resistor in your circuit. So we could have just fried all 3 of these LEDs. These might have fried instantly, and everything was forced across this one. So we've got to now troubleshoot. So that's one common thing. This is why we use drop resistors when we do this. All right, the resistor, we got to limit the current flow. These guys can't handle immediate current. We have to limit the current. All right, this is just a 200 ohm resistor, but if you don't do it, they're not going to work. So went ahead and replaced them. It's a common mistake. All right, I just wanted to show you guys what happens and why it doesn't work. So it's part of troubleshooting. These are like 6 cents a piece. So these were the sacrificial lambs for today to remind you that we have the drop resistor. I also talked about it in the series resistor circuit, but wanted to show you why. All right, you can't smell it here. They smell really bad when you do that, and eventually, if you give them enough, the heads will actually blow off if I actually stepped up the voltage to start with. But these two didn't even come on right, and then that third one took a little while and came on. So I don't even know if I have them in the same order for you, but it's not really part of the point. The point is you have to protect every single LED with a drop resistor or it will fry instantly. And then we have to do the same thing when we're using the software on the computer. So when we use multi-sim and we create our circuits, we still need to have a resistor before each LED. And this one resistor will suffice for all three of these. It's enough to protect a current so the current doesn't spike. We have to control how much current's going into these guys. And if it's going to give it a whole bunch of current right away, these guys are going to blow. All right, so just a troubleshooting thing. All right, we're going to turn these back on now. And all I've done is added a drop resistor. So it's coming, from the positive here, dropping over into this row. The resistor is going in here. And the other end of the resistor is on the long legs of all three LEDs. The legs all have to be the same. So on this side, it's all the long legs of the LEDs, and on this side, I put all the short legs of the LEDs, if you can kind of see. All right, so we're going to turn the power back on now, and look, all the parallel lights are on. How do I know they're in parallel? What happens if I remove this one? The other two stay on, right, and this one doesn't. What happens if I put this one in backwards? Okay, backwards. It should not work, right? Because it's a diode. Diode controls the direction of current. And in this case, we have to make it more anode than cathode, or more cathode than anode, and we talk about this, all right? But, so, these are parallel. I can pull out any one of these, and the others should stay on. So if we take out the green one, those are going to stay on. So this is how your house is wired, essentially. All the lights in your house, all right, are on that circuit, and that circuit, everything is wired in parallel. So, you're in your kitchen, you got 10 lights, one goes out, you don't want all of them to go out because you can't see in the kitchen then. So you might have just one that goes out. So this is, all right, parallel breadboarding. So we're going to step it up and read the voltage drop here in a minute, and we will read current through each branch. Remember, there's branch currents now. So this is the total current that's going through the resistor, and then that total current is going to branch into each one of these LEDs. In our scenario, the current should be the same through each LED because the resistance level through each LED is the same. So I should get pretty close to the same reading. Now, I can tell by the luminosity of these, all right, that one might have a little bit more resistance than the other. But we'll take a look when we put the meter on. All right, now we're going to take a look at the voltage drop across each one of these. I'm applying a power supply voltage of 6 volts here. So the total voltage drop across this resistor plus these guys, we're going to have to add up to about 6. All right, I'm assuming my power supply is working correctly. All right, so this, all right, is 4 volts across the resistor. So 4 of the volts are dropping right across the resistor, and we can calculate the current off of that in a little bit. But if you notice, I'm going to try to do the best I can here to show you we can get across each leg here. And notice we're about 1.9. It's, we need to get to 2, but that's close enough. So 1.9, and then I'm going to measure across this LED, 1.9, and then I'm going to measure across the last LED, and that's 1.9, right? The voltage drops across each element in parallel are the same. So we saw that each voltage drop, all right, across each one of these LEDs is 1.9 volts. What's the total voltage drop across this system, right? I got to go from this leg of the resistor to this leg of the resistor. It's 6 volts. That's what my power supply is sitting at. So the total voltage drop, all right, it's because, we're using a certain amount of decimal places, but, right, remember the resistor here ended up being 4 volts. So, I mean, essentially we're getting, 5.9, but when we go across the whole thing, we get the entire 6 volt drop that goes across right here. So, in parallel, all the elements in parallel have to what? Have the same voltage drop across them. And this is actually a series parallel connection. The LEDs are in parallel with each other, but this is a series parallel combination circuit, the way I wrote this up. I could have put the resistor in parallel with the LEDs and we would have been fine, but or given each one its own resistor, we could have done this well. But technically, this is a series connection in with these 3 parallel. But the point I wanted you to see was these 3 LEDs are in parallel. And that's the important part. And being able to read and take an accurate voltage drop across parallel. So whether we're doing the total voltage drop, right? Or the individual voltage drops. And we can calculate all of that in theory as well. So this is a 6 ohm resistor, or not a 6 ohm, a 200 ohm resistor. We did that in the series circuit. See, look, this is why I can't read resistance right now because we got current going through it. So remember, to read resistance, we had to come out and switch the meter to ohms, right? I can use my fingers on this one. It should work. I don't have enough resistance going for me. All right, so if I hold this down on here, all right, this resistor, 197.6. So we call that a 200 ohm resistor. So there's double checking. Remember, the resistor cannot be connected. I have the same size resistor here that's in the circuit, but remember, to read resistance, the resistor cannot be connected to the circuit. It's literally just connected to the prongs on the end of the probes right here, and I'm physically holding them down with my thumb. So I'm reading the total resistance here of this resistor, same resistor that's down in here. So now we've covered voltage, drop, and resistance. We'll take a look at how to read current. All right, well, now we're going to read current here in our series parallel circuit. All right, so the first thing that we're going to read is the total current. So what I'm doing is I'm coming in over here from the plus, the red over here, and I'm going to put it in one of the holes in the breadboard over here. We're going to go through the multimeter, out of the multimeter, and into the other part of the circuit to complete the pass. So if you take a look here, please remember on your meter that you have to remove it. So over here, this reads ohms and voltage, and then we have to move it over here into the two correct places to read current. I'm reading low current, so we're going to go in here. This has a much higher fuse if we're reading full, anything over an amp or up to 20 amps without blowing the fuse, okay? So make sure that we're reading the meter correctly. I'm going to have it set to 200 milliamps when we read the current. So when I'm going to come over here and put the power on, and we can actually take the reading here and see as it comes on the screen. So once again, this is reading total current. So I've stepped into the circuit. I've put the multimeter in series with the circuit. So nothing's going to work, all right, unless I put the multimeter in the series with the circuit. All right, because watch, if I turn the multimeter off, I have the power supply on, I turn the multimeter off, the circuit doesn't work because it's in series with this resistor, and I'm reading the total current right now. So, but the second I turn the multimeter on, and I'm able to pull current over here, okay, and I'm in the right setting, now the current has to go through here, through the multimeter, out of the multimeter here, and then split into the resistor and the 3 LEDs. So the total current in this circuit right here, okay, I'm set down here on milliamps, so I'm at 20 milliamps. I can read up to 200 milliamps down here where I have the meter sitting. So right now I'm at 20 milliamps. That's the total current. All right, so now there's going to be different current in each branch. So I'm going to kind of show how that works. Okay, so now we've made some adaptive changes here to the circuit just to show you what's going on. All right, I've moved the resistor up here. Now I'm reading on the other side of the resistor, and I'm reading through the power, through the resistor, into and through the multimeter, out of the multimeter, and to each one of the LEDs. All I did was move the multimeter so it's on the other side of the resistor. Well, why didn't the current change? It's still 20.2 milliamps. Because I'm still in series and there's still this resistance. This is total current on the circuit, right? So whether I'm on this side of the resistor or this side of the resistor, the total current should remain the same. Where it's going to vary now is when we go into the parallel branches. All right, so I'm going to make some changes so that we can truly see different current here. So I'm going to add a couple different resistors on here. So I went and grabbed a few more that we're going to run through so that we will get different current through here. So I had to change up how we did this a little bit. All right, and we'll zoom in here real quickly and kind of take a look at the different connections that we have here on the circuit. All right, so what's different is how we make the connections. So right here, the short leg of all these 3 LEDs are still in the same hole. It has to be that way. But I had to stagger them up here so that I could go through each resistor. So the amber LED is staggered up here. the green LED is staggered here, and the red LED is staggered here. Here's what makes it still in parallel. What's feeding each one of these legs is coming from the same locale here. So I'm going through a resistor, resistor, resistor now for each LED, but these legs are all the same. So since these are all in the same spot, these are all the same spot, everything's parallel. So when I plug this in, all right, we should get lights to turn on, and I give them power. So now this is a true parallel circuit. Okay, these are all in parallel. Everybody's got their own drop resistor. So when we do this, all right, I eliminated that series piece now, and each one of these voltage drops will be slightly different because of this, but that'll be in parallel. So the total voltage drop across here will be the same because they're all in parallel, okay? But the resistance piece won't be the same, okay? So this voltage drop across here to here will be the same. This voltage drop across here to here will be the same. This one will be the same, but across the resistors, it's not going to be the same. Just this total volume, because this resistor is in series with this LED. This resistor is in series with this LED. This resistor is in series with this LED. But these as a whole, this combo is this series connection is in parallel with this series connection, and in parallel with this series connection. All right, so we're gonna go through now and take a few look at the current. Okay, here's the setup for how we're gonna read the current through one branch. Okay, I'm gonna zoom in so that you can take a look. What I had to do, all right, is put the ammeter in series with one of the branches. All right, so this piece, when you zoom out, it's going to come in. It's still the same node right here for all three of these resistors. All right, so I moved the leg of one of these resistors here, just back a little bit and staggered it. The LEDs are in the same formation we just talked about, but I staggered this resistor. So now I come out of this resistor through the multimeter, back out of the multimeter, and then through this LED. So this is how we're going to read the current through this branch of the parallel circuit. All right, so if I look, all right, we can see that we're reading, 13.4, 13.5, and I'm down here in milliamps. Okay, now we're going to take the reading on the middle one. So here's the setup on the middle one. Okay, now the middle resistor I've staggered. Everybody is still coming in to this node here, so this connection, this connection, this connection, they're all the same. All right, the original resistor I put back and connected over here so that it's in series with this LED. And now what we've done is we've bypassed, so we've shortened up where this resistor right here goes, where it's coming into this red wire is going into the multimeter, coming out of the multimeter through the blue wire and connecting to this LED. So what we're going to do, okay, is if we scroll back out here and take a look, all right, you're running at 17.5 milliamps. Okay, so this one's at 17.5 milliamps. So there's more current going through here, which means what? This resistor over here is a larger one. I think I picked like a 370 or a 320 on that one. Okay, and then lastly, we'll read the current out of the last branch, and then we'll read the total current so that those three individual currents should add to the total current based on Kirchhoff's current law. And lastly, the setup on this other branch, the setup on the other branch goes as these guys are still all in the same locale. We've shortened this resistor down, so I'm coming from this resistor into the blue wire here, into the multimeter, out through the blue wire here, okay, and into the LED. So now I have my ammeter, or it's my multimeter, but I'm reading current. This part, the multimeter is in series with this resistor, but I'm reading the parallel branch here. So when we zoom back out, all right, notice this one is roughly at 19.6 milliamps. So this one has the most current going through it. This one has the least. What does that tell me? This resistor is smaller than this resistor. Notice I have three different resistor values now. Okay, so that's the important piece. Three different resistor values. So I have three different branch currents. So all three of those, when I take the total current here, should add up to the total current. So I'm going to set that up real quick and we'll walk through it. All right, still working with the same setup now, and now we're back to the original configuration as we go through this. The original configuration was where we have these three branches all in parallel with each other, and the resistors in series with the light, all right, in each one, but all the resistor LED combination, this one's in parallel with this one, which is in parallel with this one, okay? So now we have it set up so we can read the total current in this case. So it's a little different from the video I started out with. I added more resistors so we could really make sure that we see the different current value. So now power is going to come in through over here, go through the multimeter, all right, come out of the multimeter here, all right, and we're going to, there's where it's going to branch. Now if we look at the multimeter reading, it's reading 48.9 milliamps. So if we added up the individual ones, I think it's like 13, 17, and 19-ish. If we add those up, we should get 48.9 milliamps. And it's going to be off just a little bit based on the tolerance of like our theory. But there's how we're reading current in a parallel circuit. All right, so let's just take a look at voltage drop readings real quick. All right, my power supply, I'm going to tell you we're putting off 6 volts over here on my power supply. So we should be able to take the readings. So when I said the voltage drop across this branch is 6 volts, the voltage drop across this branch is 6 volts, and the voltage drop across this branch is 6 volts. So these are all in parallel. So the voltage drop from here to here, here to here, and here to here is 6 volts. Now, here's what's different though. Since the resistor's in series, it's going to have a 4 volt drop. And then if I read across the LED, we'll have approximately a 2 volt drop. So this 4 plus 2 is 6. Look, if we read across this resistor has a 3.8 drop, right? This LED has like a 2.1. Okay, so the voltage drop from across this resistor is different than the voltage drop across this resistor and LED because these guys are in series. But notice that series has to add up. So regardless of if this is 3.8 and if this is 2.0, right, it's going to give us 5.8. But if we read the voltage drop across here, we should get to 6. That's the exact voltage drop. And if we read the voltage drop across this resistor, okay, we're getting 3.9. And we're getting the voltage drop across this LED here is 2. So they're all approximately close, right? So we got KVL and KCL all working for us here. So that's the total voltage drop and how we read the parallel voltage. So no matter what, I showed you that these were different resistor values because you saw that based on the current. So based on different resistor values, right, and these guys being in parallel all together, all right, the sum of these voltage drops in series have to equal this total voltage drop, which is 6 volts. And since all 3 of these branches are in parallel with each other, they all have the same voltage drop, and that's my applied voltage. So if I step the voltage up a little bit, all right, you can see, all right, I stepped it up to 9. So now the voltage drop is 9 volts across each one of these branches approximately. All right. So no matter what I supply, that's my voltage source. And we'll talk about that when we start being able to do our voltage divider circuits.